Hello, everyone. My name is Shreyans Daga, and for my fifth or second milestone video, I decided to make my robot actually move and um, travel to my object, and we also implemented the code to actually for the robotic arm to actually go in and pick up the object. So the movement code was relatively simple to implement. Uh, uh, because we just at the top we just initialized some pins and we just set up our motors as outputs, and then we just created functions for each motor that allowed us to tell them to rotate at a particular PWM. And we did that for each motor, the left motor and the right motor, because there's two motors on the robot. And then I implemented a move function that allowed me to move either in any direction in just a simple one line command. And so the movement code was relatively simple to implement, but I was having trouble turning the robot left to right because in this version of the robot, to turn left to right, you have to turn these wheels, the front wheels, left or right. And this was challenging to do because we hadn't yet figured out how to control servos, and the front wheels are actually rotated using a servo. And so we had to figure that out, and we ended up finding this Adafruit Servo Kit library, which just allows you to get a list of all of the servos plugged into your Raspberry Pi, and then it's relatively simple to control them. You just have to access which servo you want to control, and then what angle you want to set it to. And so, depending on which direction we want to travel in, right, left, or straight, we set the front servo to a particular angle. And so once we had that figured out, we were able to get the robot to travel to the object. But we still had to figure out how to pick up the object. And so the way we decided to do this was using inverse kinematics. Um, and so the way that we implemented it, or the idea of inverse kinematics, is that you know where your object is and you know where you are, so you can do some math to figure out how you need to position yourself, or rather, position your robotic arm to go and pick up the object. And so in our case, our robotic arm has two mini arms to say. This is the first arm, and this is the longer arm. This controls where the clippers are. And then we have the second part of the arm, which is this part, and this is for more fine tuning of the positioning of the robotic arm. And so what we did was that in a we created the solver function where we have the lengths of our arms, and then we have our distance that we can take in from our previous milestone where we calculated how far away we are from the object using triangular similarity. And so we can take all of these three distances and make a triangle using these three distances. And then once you have three sides of a triangle, you can use the law of cosines for the angles to try and solve for each of the angles. And each of the angles of the triangle is the angle that the servo motors need to rotate to, with a certain offset added or subtracted from that angle to account for the axis of rotation that the servos are rotating on. Because the triangle is drawn in a flat axis of rotation, but the servos rotate from an axis of rotation that is dependent on how they're positioned. So you have to take that into account when you send the servos an angle. And this was probably the hardest part so far, because it was kind of hard to conceptualize what we were actually doing, but once we had it figured out, it wasn't particularly difficult to implement it in code. Just the idea of what we were going to do was hard to come up with. Once we had that working, we moved on to making the OLED screen and the top, or on the back of our robot, which is this thing, make that work using this code right here. And then we also made our LEDs, or our sort of headlights, at the front of our robot, which is these two things, also work just as cool features to